Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Yeah.
Today's big question, why is AI so hard in physics so relatively simple?
Relatively is the key word there. I mean, physics seems simple because we've spent centuries, millennia even, distilling it down to elegant equations. But think about the sheer number of parameters involved in, say, climate modeling. That's physics, and it's hardly simple.
Yeah, but even climate modeling, complex as it is, relies on well-defined rules, right? Conservation of energy, fluid dynamics. AI, especially when we're talking about AGI, feels like we're trying to define those rules from scratch, and we're not even sure what the rules are.
Exactly. Physics has the advantage of describing a universe that, at its fundamental level, is governed by rules. AI, on the other hand, is trying to create something that mimics intelligence, which might not be rule-based in the same way. Or, at least the rules are so complex and intertwined that we can't easily extract them.
Okay, but let's dig into that a bit. And is it really that the rules are missing? Or is it that our understanding of the rules is missing? I mean, the brain is a physical system, right? It operates according to the laws of physics. So in theory, we should be able to understand it and therefore replicate it.
I think that's where deep learning comes in. It's a way of approximating those complex rules without explicitly defining them. We throw massive amounts of data at a neural network, and it learns to extract the patterns, the underlying relationships, the rules, if you will, that govern that data. It's like letting the universe program itself, and then we just copy the code.
But that's the problem, isn't it? It's just approximating. It's finding statistical correlations, not genuine understanding. A deep learning model can identify a cat in a picture with incredible accuracy, but does it know what a cat is? Can it reason about cats, make inferences about their behavior, understand their place in the world?
And that approximation breaks down when you move outside the training data, right? It's brittle. It lacks the flexibility and adaptability of a real intelligence. You know, it's like teaching a robot to navigate a specific room. It can do it perfectly, but as soon as you move a chair, it gets completely lost.
That resonates with my own thinking. It's like current deep learning feels a bit like brute force pattern recognition. I wonder if focusing on building AI models that emulate specific neurochemical processes in the brain could unlock a different path towards true intelligence.
But isn't that what we're already doing, in a way? Neural networks are inspired by the structure of the brain. We're just scaling them up, making them more complex, feeding them more data. I think we're on the right track, even if it feels like a slow and arduous journey. The exponential growth of data and the sophistication of deep learning models is quite impressive, but maybe they do not necessarily reflect a genuine understanding of the problem.
I'm not convinced. I think we need to step back and consider alternative approaches. Deep learning is good at pattern recognition, but it's terrible at symbolic reasoning. It can't manipulate abstract concepts, make logical deductions, or understand cause and effect. We need something that combines the strengths of neural networks with the power of symbolic AI.
I agree. I think the key is in understanding how the brain represents and manipulates information in different coordinate systems. Think about how we navigate the world. We have a spatial sense, a temporal sense, a sense of our own bodies in space, and we can seamlessly translate between these different representations. Current AI struggles with that.
That's a fascinating point, Donald. So you're saying it's not just about processing information, but also about understanding its context, its spatial and temporal relationships.
Well, deep learning can handle sequential data through recurrent neural networks and transformers. They're used in natural language processing all the time to understand the context of words in a sentence. Isn't that a form of spatiotemporal reasoning?
But it's still just pattern matching, right? It's learning the statistical probabilities of words appearing in sequence. It doesn't understand the meaning behind those words, the underlying concepts they represent. It's like teaching a parrot to recite Shakespeare. It can do it perfectly, but it doesn't understand a word of it.
Exactly. And that's where the coordinate translation comes in. Imagine you're looking at a map. You can zoom in to see the details of a street, or zoom out to see the entire city. You're shifting between different scales, different coordinate systems, and you understand how those different views relate to each other. Current AI can't do that. It's stuck at one scale, one perspective.
Okay, let's think about a real-world example. Self-driving cars. They rely heavily on deep learning for object recognition and scene understanding, but they still struggle with unexpected situations, like a pedestrian suddenly stepping into the road. Is that a failure of pattern recognition or a failure of spatiotemporal reasoning?
I think it's a combination of both. The car needs to recognize the pedestrian, but it also needs to predict their trajectory, their intent, their relationship to the environment. And that requires understanding the dynamics of the scene, the flow of traffic, the rules of the road.
And it needs to be able to reason about those things in a symbolic way. If the pedestrian is close to the curb and facing the road, they are likely to step into the road. That's a simple rule, but current AI struggles to represent and apply rules like that in a flexible and robust way.
And it needs to do it in real time, under pressure, with incomplete information. It needs to be able to translate between the raw sensory data from the cameras and sensors and the abstract concepts of pedestrian road safe distance. It's a massive coordinate transformation problem.
So going back to the original question, why is AI hard and physics simple? It seems like physics deals with well-defined systems where the rules are known even if they're complex. AI, on the other hand, is trying to create intelligence, which might not be rule-based in the same way, or where the rules are so complex that we can't easily extract them. And that's compounded by the challenge of representing and manipulating information in different coordinate systems.
I still think deep learning is a key piece of the puzzle. It's a powerful tool for extracting patterns from data, and I believe it can be used to approximate the complex rules that govern intelligence. But I agree that we need to go beyond brute force approaches and incorporate more structured knowledge and reasoning.
I think we need to prioritize symbolic AI and neuro-symbolic approaches. We need to develop algorithms that can explicitly represent knowledge, reason logically, and make inferences. And we need to find ways to integrate those algorithms with the pattern recognition capabilities of neural networks.
I think we need to focus on understanding how the brain represents and manipulates information in different coordinate systems. We need to develop algorithms that can seamlessly translate between different scales, different perspectives, different representations of space and time. That's the key to building truly intelligent machines.
It's interesting how the seeming simplicity of physics, with its elegant mathematical formulations, might actually mask a profound underlying complexity, much like how current AI approaches might be scratching the surface of a far deeper problem. Perhaps the difference is that in physics, we've had centuries to refine our understanding and develop appropriate abstractions. With AI, we're still in the early stages, grappling with the raw complexity of intelligence itself. This makes me think of the contrast between the perceived complexity of AI and the apparent simplicity of some physical laws, and that it might stem from a fundamental misunderstanding. Physics often deals with well-defined, static systems. AI, on the other hand, is about dynamic, changing systems with a vast number of variables. Perhaps the seeming simplicity of physics is an illusion of abstraction, and the true complexity of the universe is masked by simplifying assumptions.
Yeah, it's easy to look at an equation like E max C and think, wow, that's simple. But that equation represents a vast amount of underlying physics, a whole universe of interactions. And the same is true of AI. A simple neural network might seem straightforward, but it can learn to perform incredibly complex tasks.
But the simplicity of EMXE is that it captures a fundamental relationship. It's not just a statistical correlation, it's a law of nature. Deep learning models, on the other hand, are often just capturing statistical correlations. They're not uncovering fundamental laws.
And that's why they're so brittle. They're not grounded in reality. They're just learning to mimic patterns in the data. They don't understand the underlying principles that generate those patterns. And without that understanding, they can't generalize to new situations.
Okay, so let's shift gears slightly. What are some specific research directions that each of you thinks are particularly promising given this discussion?
I think we need to explore more sophisticated architectures for deep learning, architectures that can handle more complex relationships and reason about abstract concepts. Things like graph neural networks and attention mechanisms are promising, but we need to push them further. I need to investigate further the potential of using deep learning for encoding spatiotemporal information and how well it can translate between different coordinate representations, for example. Pixel-based, relational. This could be key to moving beyond the current brute force approach to achieving a truly intelligent agent.
I think we need to develop better ways to integrate symbolic reasoning with neural networks. Things like neuro-symbolic programming and differentiable logic are promising, but they're still in their early stages. I need to explore how symbolic reasoning can be integrated with neural networks to create more flexible and robust AI systems.
I think we need to study how the brain represents and manipulates information in different coordinate systems. We need to develop algorithms that can learn to translate between different scales, different perspectives, different representations of space and time. That's the key to building truly intelligent machines. It's interesting to consider whether there are inherent limits to what deep learning can achieve. Is there a point of diminishing returns regarding data-driven brute force when dealing with abstract concepts and spatiotemporal reasoning?
From my perspective, I think we need to look more closely at the neurochemical processes in the brain. How do neurotransmitters and neuromodulators affect learning and decision making? Can we build AI models that emulate those processes rather than just focusing on the structure of neural networks? Also, how can we bridge the gap between the highly distributed representations in neural networks and the more localized symbolic representations used in cognitive models? This seems crucial for building AI systems that can reason about abstract concepts and make inferences.
That's interesting. So you're suggesting a more biologically inspired approach, going beyond just mimicking the structure of the brain and trying to mimic its function as well?
Exactly. The brain isn't just a network of neurons. It's a complex chemical soup with a vast array of signaling molecules that modulate neural activity. I think we're missing a crucial piece of the puzzle by ignoring that aspect of brain function.
And that could also help with the explainability problem. If we understand the underlying mechanisms of our AI models, we can better understand why they're making the decisions they're making.
And it could also help with the robustness problem. If our AI models are grounded in real-world principles, they're less likely to break down in unexpected situations.
Exactly. It's about building AI that's not just good at pattern recognition, but that's also grounded in reality, that understands the underlying principles that govern the world. Because if AI is so hard, why are there parallels in neuroscience that might be offering clues to how biological intelligence works? Perhaps by studying how the brain encodes and processes information in different coordinates, spatiotemporal, feature-based, etc., we can find better ways to combine these into computational models.
So, to summarize, we've identified several key challenges in AI: the need for more structured knowledge and reasoning, the challenge of representing and manipulating information in different coordinate systems, and the importance of understanding the neurochemical processes in the brain. And we've suggested several promising research directions developing more sophisticated deep learning architectures, integrating symbolic reasoning with neural networks, studying the brain's coordinate transformations, and emulating the neurochemical processes in the brain.
And the underlying theme is that AI is hard because we're trying to create something that mimics intelligence, which might not be rule-based in the same way as the system studied in physics. Or at least the rules are so complex and intertwined that we can't easily extract them. It is crucial to look beyond the superficial successes of current deep learning models, and we need a deep-seated need for a framework that explicitly handles knowledge and reasoning, a need that contemporary neural networks seem to largely ignore.
And that the core problem of AGI is not just about building a better algorithm, but also about designing a framework where algorithms can learn to actively interpret and manipulate the very concept of space and time.
Well, that's all the time we have for today. Thank you all for listening to Cognitive Spirals. We hope you found this discussion informative and thought-provoking. Join us next time for another deep dive into the fascinating world of consciousness, cognition, and machine intelligence.